Alrighty, so today we are going to continue with some application problems for exponential and log functions. Throughout your notes, next to the three boxes that we're going to work with, you're going to see use this when it says equation 1, use this when it says equation 2. So you want to make sure you're paying attention on the homework as to why I'm telling you to use that equation. Okay, so you want to think through that. So our first equation that we are going to talk about today is the basic exponential equation. So that is the equation y equals a times b to the x power. Okay, this is the one you've seen before. This is the one you're really comfortable with. A is the initial or starting value, and B is the constant multiplier. Okay, your key words for this formula are going to be the words doubles, triples, halves, anything like that that's telling you that something is happening at a consistent pattern. All right, so let's look at number 1. Suppose that you are observing the behavior of cell duplication in a lab. In one experiment, you started with 100,000 cells and observed that the population decreased by half every minute. So this by half right here, that's what's telling us that we're going to use this equation, that we're going in the same pattern, okay? What is this 100,000 going to be? That's our starting value. So part A tells us that we're going to write an equation. So we want y equals our starting value, which is 100,000, times 1/2, and they want us to use t for time for minutes. Okay, and we want to determine the number of cells after 10 minutes. So what are we going to plug in? 10 for t. So y equals 100,000 times 1/2 to the 10 power. I'm not going to pull up the calculator for fear that it will crash the recording. But so you do this on your calculator. 100,000 times 1/2 to the 10 power. All right. So we get 97.656 cells. Part C says determine how long it would take the population to reach 10 cells. So we're going to plug in 10 here for what? Y. So 10 equals 100,000 times 1/2 to the t power. Okay? Eventually, yes, we're going to change this to a log because we are solving for an exponent. But first, remember, we have to isolate that exponential. Good. So divide by 100,000 first. Okay, we get 1 0 that cancels on each of those. So we get that 1 over 10,000 is equal to 1/2 to the t power. Everyone okay? All right. So from here, we're solving for an exponent, so we're going to rewrite it as a log. So what would that be here? Log base 1/2 of 1 over 10,000 equals t. All right, then remember our change of base formula. So you take your log of your argument, so log of 1 over 10,000 divided by log of 1/2. And that's what you're entering in your calculator. So everyone should be practicing entering these things in because I want to make sure you can get the correct answers. So you're entering this in on your calculator. And you get 13.288. And what would our units be? Minutes. Check what you typed in. Make sure you did it in the correct order. Make sure you did log of your argument over log of your base. Okay, let's go to our next equation for today. This one is the value, appreciation, and depreciation formula. This is very, very similar to our equation for interest, compound interest, but it doesn't have to specifically do with base, okay? It has to do with any time the value is appreciating or depreciating.
We have to know all these formulas plus the interest formulas.
You do need to know the formulas, yes, okay?
They're not given to us.
You do need to know your formulas, right? You need to have those memorized. You need to know when to use which ones. Okay, so here's our appreciation depreciation formula. It's A equals P times 1 plus or minus R to the T power. All right, the key words are appreciation, depreciation, value, and then also the words increase and decrease. Okay? A, P, R, and T are pretty much the same thing that they were in our interest formula. A is the total or the final amount. P is our starting amount or initial. R is the rate of appreciation or depreciation. And T is our time. Let's talk about this plus or minus right here. Are we going to do both in the same equation?
No, we're going to separate.
No. One represents appreciation. One represents depreciation. So you're going to use plus if the problem is talking about appreciating, and you're going to use minus if the problem is talking about depreciating. You just have to think through, are you adding or subtracting? Okay? All right. Shawnee Middle School found that in its enrollment, it was increasing at a rate of 1.5% annually. In 2011, the enrollment was 1,200 students. What will be the total enrollment in 2017? So let's see what we've got. We've got this 1.5%. Okay, so our R still has to be given as a decimal. So if you want to write that up here as a decimal, that's probably a good plan. So here our R is going to be 0.015. This annually tells us that our time is in years. But for these formulas, your time does not always have to be in years. Okay, it just happens to be in this problem. Okay, in 2011, it was 1,200 students, so that's our p-value. What will the total be? So that's asking us to find A. And 2017 tells us that our time is 6 years. Okay, is this appreciating or depreciating? Appreciating. So we're going to use our addition. So A equals P times 1 plus R to the T power. So A equals 1,200 times 1 plus 0.015 to the 6th power. Can we simplify 1 plus 0.015? Yeah. You don't have to. It's just a little bit easier when you put it in your calculator. All right, go ahead and put that into your calculator. And these are talking about people, so let's round to the nearest whole person. All right, when you type it in, you should get 1312.132. So we're going to say 1312, and we are talking about students.
So, if that was my test, would you have to do 13 and still get credit? Because you can't, if it's more than a person, so you'd have to round down.
Yeah, that'd be fine. Okay. Identify your variables and set up your equation in number 3. Identify your variables and set up your equation for number 3, please. Quickly, without talking. All right, 120 milligrams. What does that represent? The starting amount, P. Eliminated. What that tells me is that we're using our depreciation, right? We're going down. A rate of 15%, so R is 0.15. Hours tells me that my time is going to be in hours. Okay? How many hours would it take for half the medicine to be eliminated? So that tells me that A is 60. Okay? And how many hours tells me that we're looking for T. All right, let's plug in. 60 equals 120 times 1 minus 0.15 to the T power. We are solving for an exponent. Anytime we are solving for an exponent, we have to rewrite it as a log. But before we can do that, we have to isolate that exponential part. So we divide both sides by 120, which will give us 1/2 equals, what's 1 minus 0.15? 0.85 to the T power. All right, again, we're solving for an exponent, so we need to rewrite this as a log. So log base 0.85 of 1/2 equals T. Change of base formula. How do I do that? Log of the argument, so log of 1/2, over log of the base, so log of 0.85 is equal to T. Let's round to the nearest thousandth of an hour. Thousandth of an hour. What about it? What do we get? Hours. Good. Please don't forget your units. Your units are important here. All right, let's look at number 4. All right, Margaret Madison, DDS, estimates that her dental equipment loses 1/6 of its value each year. So again, we see that word value. That's a hint to us, okay? And loses tells us it's depreciating. Instead of using a rate as a decimal, they gave us a rate as a fraction. That's okay. Decimals and fractions work the same way, okay? So if we write an equation to represent this, This would be A equals P times 1 minus what?
R.
Okay, and what would R be in this case? 1/6 to the T power. So if you wanted to, you could simplify that to A equals P times 5/6 to the T power. All right? We're going to skip over B. That's just plugging in. We can handle that. Let's look at C. Determine how long until the machine is worth less than $30,000. So we're going to use this cost right here. It's $175,000 new. Okay? And we want to know when the machine is less than $30,000. So could we find when the machine is exactly $30,000 and then do any time after that?
Yes.
Yeah, because the value keeps going on, right? So let's say that 30,000 is equal to our principal, which is 175,000, times 5/6 to the T power. What would we do first? All right, divide by 175,000. Now, when you divide that in your calculator, you get an ugly decimal. Do not round that decimal. But you also don't really want to write that whole decimal out. So instead, turn it into a fraction. How do you turn it into a fraction?
Math fraction.
Math frac, which will give you 6 over 35. So 6 over 35 is equal to 5/6 to the T power. All right, we're solving for an exponent, which means we need to rewrite as a log. So log base 5/6 of 6 over 35 equals T. All right, please use your change of base formula. Be careful with your parentheses. And let's round to the nearest thousandth of a year. All right, so after how long?
9.673.
Yeah, so more than 9.673 years, after 9.673 years, something along those lines. Okay, make sure that you are practicing putting these into your calculator, so you are making sure you're able to get these correct answers. Okay, this next formula is very much like our compounded continuously formula. It's essentially the exact same thing. It's just used in a little bit different way, with a little bit different variables when we're talking about exponential growth or decay mainly with populations or with elements. Okay, so it's pretty specific. So this formula uses different variables. Y equals C times E to the KT power. All right. Y is going to be the final amount. C is going to be the initial amount. E we know is not a variable, right? It's our natural number. Okay, it's a constant. K is going to be the constant specific to that problem. And T is going to be your time.
So you're going to give us these garbage times. Or are you going to give us, you said on the homework you're going to write equation 1.
Yeah, on the homework there are hints, but you need to use those hints to help you memorize when should you use which formula. Okay? It will not tell you which formula to use on tests or quizzes. You get the problem wrong if you use the wrong formula. Okay? All right, a city in Texas had a population of 75,000 in 1970 and a population of 200,000 in 1995. The growth between the years of 1970 and 1995 followed an exponential pattern. Okay? So we're going to write a model or an equation that estimates the population at any time during those years. So first thing we have to find that we don't know yet is the K, the constant. Okay? So we're going to start by solving for K. So we need to plug in what we know. We know we end up with 200,000 people. We know we start with 75,000 people. And we know that this takes place over 25 years. What we don't know is the K. That's what we're looking for. Okay? How do we solve for that K? Divide both sides by 75,000. So go ahead and divide that and turn it into a simplified fraction. What does that give you? 8/3 equals e to the 25k. All right, what are we ready to do now? Good. Rewrite it as a log because we are solving for k, which is in the exponent. Okay? So log base what? E. So when we have a log base e, that's our natural log of 8/3 equals 25k. And then what? Divide by 25. Okay, now when you get k, obviously the best thing would be to use not a rounded version and just store it and all that stuff. But for sake of writing it down, we can't do that. Okay, so it's okay to round it. We're going to go ahead and round a little bit farther than we normally would, though. So we're going to go to 4 or 5 decimal places. Let's go to 4 for right now, 0.0392. Okay, because we want our answer to be as close as possible. Okay, so that means we can now write the equation now that we have k and we have our initial. So y equals, our initial population is 75,000 times e to the 0.0392 t power. Okay, from this model, estimate the population for the year 2010. So if the year is 2010, what does that mean our t is? 40. Why 40? Good, because t here represents the number of years since 1970. Okay, so y equals 75,000 times e to the 0.0392 times 40 power. Make sure if you have the older operating system that you put this exponent in parentheses. And let's round to the nearest whole person. What do we get? 359,778 people. Make sure you can get that answer. Okay. Another situation where this is used is with half-lives, which you've studied in chemistry, I'm sure. Okay? At some point, you have studied half-lives. Half-lives basically tell you the length of time it takes for half of a given substance to disintegrate. Okay? So carbon-14 has a half-life. Please stop talking. Carbon-14 has a half-life of 5,760 years. So what that means is that every 5,060 years, half of a mass of carbon-14 disintegrates, okay? It's what like carbon dating is based off when they find a really, really old fossil, okay? So we need to find the value of K for this equation so that we can write the equation of decay for carbon-14. So basically, we know that to get half of a mass, so if we start with 1 and we get a half, times e to the k, and then we know our t is 5,760. All right, so this means that we need to use a natural log. So the natural log of 1/2 would give us 5760k. If we divide both sides by 5760, we'll get our constant. When you get that constant, if you type that in your calculator, you get e negative 4. What does that mean? Times 10 to the negative 4th. So you need to move your decimal point 4 places, to the left. So you should get negative 0.00012, which means that the equation of decay for carbon-14 is y equals c times e to the negative 0.00012 times t power. And then you could continue to plug in from there.